This lesson is on trigonometry. It's the study of measuring parts of triangles. Let's look at the anatomy of a right triangle. So, we have a right triangle, we have 90 degrees in the corner here. Across from the 90 degrees is always called the hypotenuse. Now, if we chose this tip here, where the lady is looking, and we chose that to be our angle of reference, so here's our reference angle, then exactly the side that she is looking at is called the opposite side because it's opposite to the angle of reference. The side that is adjacent to the reference angle is called the adjacent. So understanding these names is going to be really important in forming the proper proportions that we will need. Here's an example of a right-angled triangle. Our angle of reference is A, and our angle of reference is chosen in this way because our opposite, our adjacent, and hypotenuse are labeled according to it. In this case, at this point in time, angle A is 30 degrees. We have also measured every side, and we're also considering the relationships between those sides. Now first take a look at what happens if I drag this triangle around. My angle stays the same. It's constantly 30 degrees, but my sides are changing. However, you can see that this triangle here is proportional to this triangle here. It's just as multiplied by a scale factor. So say this one side here, the adjacent is 3.8. I could multiply it by something here to get 8.3 in the same way that the opposite was multiplied. So it's just either expansion, enlargement, or shrinking of the same proportions. So since the proportions are the same between the sides, that means when we divide different combinations of the sides, we should get the same numbers for any of these triangles. Notice that that's true. I've programmed it to calculate the ratio of the opposite to the hypotenuse, the adjacent to the hypotenuse, and the opposite to the adjacent sides. So notice that the ratios are not changing at all, no matter where I place or shrink or enlarge this triangle, because as long as our reference angle is 30 degrees, our opposite over hypotenuse is always going to be 0.5. And same with the other ratios. So this will actually help us to find other parts of the triangle if we know that, hey, if we have 30 degrees here, I know my opposite over my hypotenuse is always going to be 0.5. So if, say, I knew my opposite was 1, then I would know that the hypotenuse would have to be 2, so that 1 over 2 makes 0.5. This is the essence of trigonometry here. You've probably heard of the terminology sine, cosine, and tangent. That terminology is merely a labeling of these proportions. So sine has been chosen to represent the opposite over the hypotenuse. Cosine has been chosen to relate the adjacent over the hypotenuse. And tangent has been chosen to relate the opposite over the adjacent. The equation here could be written as sine of 30 degrees is equal to 0.5. Now check that on your calculator. All of these proportions are stored in your calculator. Type in sine of 30. What do you get? You get 0.5. Similarly, cosine of 30 should be 0.866. Tangent of 30 should be 0.7578, and so on. Now, everything changes if we change the angle. Notice our ratios completely change. But if it's a different angle, then we can base it on that angle. So now if you could have sine of 10, and that should give you 0.177. So this is how trig is going to work. We're going to be looking at these ratios and comparing them to what kind of triangle we have. Maybe we have a smaller version of the triangle or a bigger version of the triangle, but the sides are lying in the same proportions. One way of remembering these ratios is SOHCAHTOA. So this helps you remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is the opposite over the adjacent. Here's a problem. We want to find the length across the lake. We have a lake. We can't walk across the lake, but we can walk in a 90-degree triangle to make the length of the lake one of the sides of our triangle. So in this case, the length of the lake is our hypotenuse. And we don't know it, so it's called x. And say we measured this angle here to be 30 degrees. And the opposite side of 30 degrees we measured to be 6 kilometers. So, can we find the length of the lake? Well, we sure can. We know that when we relate the opposite and the hypotenuse, that was our sine from SOHCAHTOA, we know that we're taking the sine ratio of 30 degrees. And we know that the sine ratio of 30 degrees should be 6 kilometers over the hypotenuse x. Now we also know from the previous example that the sine ratio of 30 degrees was always 0.5. So this is going to actually help us because we'll be able to find the length of the lake by solving this proportion. And this is exactly what trigonometry is all about. We look at what sides we have. We look at our database of ratios that we know that we can call up. And we can relate our example to the known proportion that we know is always the same for triangles of 30 degrees. So 0.5 is actually 1/2. So you can solve this using cross multiply and divide, or you can just see that 6 over what would be 0.5? 6 over 12. We know x would be 12. So the lake is going to be 12 kilometers across. Let's look at some further examples. Here we have a triangle, a right triangle, angle 50 in the top corner. So the first step is always to label our sides. That way we can determine which ratio it is. I'll write up SOHCAHTOA up here. This just reminds us that the sine of an angle is the opposite over the hypotenuse. The cosine of an angle is the adjacent over hypotenuse, and the tan of an angle is the opposite over the adjacent. So let's label our sides. Across from the 90 is always our hypotenuse. Across from our reference angle is always our opposite, and the adjacent is what's left. So we've labeled our sides. Now you want to choose your ratio. So, how do we choose? Well, sometimes you have all the ratios possible if all the sides are given, but here we only have 2 sides in question. We're not really interested in the opposite, but we are interested in the adjacent and the hypotenuse. So we look for the ratio that relates the adjacent and hypotenuse so that we include our x in our ratio and we have all the other components filled in. So let's fill in our info to our cosine equation, which would be the cosine of an angle 50 degrees. Now this is not cosine times 50, this is cosine of 50. This is a language that calls up from your calculator the question of what is the proportion of the adjacent over the hypotenuse in any triangle that has a 50-degree reference angle. And we know that in our picture, our cosine of 50 is relating our adjacent, which is our unknown, over our hypotenuse, which is 20. So this proportion should equal the grand proportion that works for all triangles of 50 degrees. So let's call that up. Go on your calculator and make sure that your calculator is in degree mode. If it's in radian mode, you'll have different answers. So type in cosine of 50 and you get 0.643. I'm going to round that. And this is the proportion that works for this ratio for 50-degree triangles. And we know that that should equal x over 20. So now we want to solve the equation. Let's get x by itself. We could multiply both sides by 20. And we get 12.855. And let's just round to one decimal place for now. So 12.9 would be our x length. Here's another example. We have 23 degrees, right-angled triangle. We want to label our sides. So across from the 90 is the hypotenuse. Across from the reference angle is the opposite. The other one's the adjacent. Now we are interested in our opposite and our hypotenuse. So from SOHCAHTOA, which just tells us the ratios and what they relate, we're going to be relating the opposite and the hypotenuse. So we want to use our sine ratio. So let's create our equation. Sine of 23 degrees is equal to the opposite over the hypotenuse, the 30 over the x. Now in this case, you'll see that our x is in the denominator. So we're just going to have to solve that. Sine of 23 is some ratio 0.3907, and you want to keep it as exact as possible. But now you want to be able to solve for x. So solving for x, you could do a long algebraic method by multiplying both sides by x and then dividing both sides by 30. And you'd notice that that would produce x equals whatever 30 divided by 0.3907 is, which is 76.8. Now, one quick hint here is sometimes it's nice to see this as a cross multiply and divide situation. It makes things a little quicker. So we're cross multiplying 30 times 1 and dividing by the sine of 23. So x is actually technically being the 30 divided by the sine 23. Depending on your calculator, you can either go 30 divided by 0.3907, or you could go 30 divided by sine of 23 directly if your calculator allows for it. Either way, you get 76.8 as your length. Now let's try this triangle. Here, they're asking us to find the angle. So there's something a little different here because we're going to be following the same process, but we're going to be finding the angle. So let's proceed as before. We're going to label our sides. Our across from 90 degrees was the hypotenuse. Our opposite is our 30 and our adjacents are 40. So the only things that we know right now are the opposite and the adjacent. If you really wanted to find the diagonal, you could use the Pythagorean theorem to find the diagonal. However, that would not tell you about the angle. So let's set up our equation. We know from SOHCAHTOA that opposite and adjacent lie under the tangent ratio. So we would have the tangent of some angle, which we don't know and is called the Greek letter theta, is equal to the opposite over the adjacent. In this case, our opposite is 30 and our adjacent's 40. So we know that the tangent of some angle is going to give us 3/4. But we don't know what that angle is. So Our calculator does, though. Our calculator has the ability to tell us what angle under the tangent ratio will give us 30 over 40. Now 30 over 40 in the calculator is stored as 0.75. So if you want to access this angle, what you need to do is tell the calculator to access it by taking the inverse operation on both sides. So what happens is we're taking theta to be tan inverse of 0.75. The inverse operation always produces us with an angle. So type that into your calculator. Somehow you need to access the inverse. Usually it's using the second function tab. It's usually right above the sign button. So tan inverse of 0.75 is approximately 36.9 degrees. Let's say that's just 37 degrees. So that's how we find an angle. We need to use the inverse ratio to eliminate the ratio and backtrack. And we're basically asking the calculator, what angle makes this work in this way? So let's proceed. Here's some more examples, things that might come up. One question would be just to find the cosine of 72. All you do is access it in your calculator, and that leaves you with 0.309. And they haven't told us to round to a certain place value. So in general, your final answers, you can round them to, say, one place value. And angles can be answered as whole numbers, unless otherwise specified. However, when you do your calculations, you want to keep them as exact as possible until you get your final answer. Here's another question. They might ask, find alpha, which is an angle because it's lying within sine, if the sine of that angle is 0.3591. So they're asking us to backtrack into what angle gave us 0.3591 with the ratio of sine opposite over hypotenuse. So in our calculators, we want to access it by using the sine inverse function, which leaves us with alpha being sine inverse of 0.3591, giving us 21 degrees. Remember to stay in degree mode. If you're not getting these numbers, then that means your calculator is not in the correct mode. Another example would be to solve the triangle. So you might be given a triangle and it says solve the triangle. What that means is find everything. Find all components. So here we have this angle, so we need to find this angle, we need to find this, and we need to find this. So let's label those. So let's label this theta and A and B. So some of the things we can do before using trigonometry include, when finding the other angle, you can use the 180 degree property. So we know the whole, all three angles need to add up to 180. So we can go 180, take away 90, take away 57. That would leave us with 33 degrees for theta. So that's done. Now to find the other sides, sometimes if you have two sides given, you could just use the Pythagorean theorem, but in this case we don't, so we need to use trigonometry. So let's call, say, the reference angle 57, and based on that reference angle, B is our opposite, 5 is our adjacent, A is our hypotenuse. So let's find B. So if we want to find B, we need to use the 5 as one of our numbers, so that would relate opposite and adjacent. Opposite and adjacent comes from tangent, from TOA. So we want to use the tangent ratio of 57 because we know that that should be the same as taking b over 5. So let's solve that. Cross multiply and divide, you get b equals 5 times tan of 57. 5 times tan of 57, using our calculator, gives us approximately 7.7 for b. 7.7 inches. And for the last one, you could either use trig or you could use the Pythagorean theorem. So because we just did trig, say you wanted to use the Pythagorean theorem. We know that 5 squared plus 7.7 squared should give us a squared. And we can solve that. So a squared should be equal to 84.2. So a should be equal to the square root of 84.2, which is 9.2. And this is how we found all the other pieces, only given 2 parts of the triangle. Here's some terminology. Some of the word problems in this section will have the following terminology used. So say there's a lady. She's got a line of sight. Now she tilts her head up to look at some birds. The angle in which she tilted her head up is called the angle of elevation. Notice it's always with the horizontal, it's never up here. Now she could also be looking down at a sailor. She could be looking down, and the angle in which she tilts her head from her line of sight downwards to the sailor is called the angle of depression. Now, the sailor also has a line of sight. If he was scoping her out, he'd have to lift his head, and that would be his angle of elevation. Notice that the angle of elevation from him to her is the same as the angle of depression from her down to him. This may be useful. Sometimes you're given this part, but you want to actually be using this triangle. Let's look at an example where we have an angle of elevation. So we have a fishing boat moving into a bay, and the captain notes that the angle of elevation to the top of the lighthouse, that is 200 feet tall, is 11 degrees. They're asking us how far is he from the lighthouse. So with these problems, the first key is to draw a picture. You want to draw out a picture so that you have a right angle triangle and you have everything labeled as best as you can. So you can practice that with more problems in your textbook. Now, let's see what we can do with this. We've got 11 degrees, so 200 is our opposite, x is our adjacent. So that's the tangent ratio. So that would be tangent of 11 degrees is going to be the same as 200 over x. Now we can solve that. Cross multiply and divide. You'll notice that x is equal to 200 over tan of 11. And somehow you can compute that in your calculator, giving you 1,028.9 feet. So that tells us that the sailor is 1,029 feet away from the bay.